kind of it's popular tool. So we analyzed, heat junction for the electroosmosis problem. So we have two reservoirs, fluid A and fluid B. So make a certain other operation at the third part. So we need to transport A. They must be at the heat junction. So this analysis is in view of this heat junction part. And as I mentioned, sometimes we need to mix certain fluid. So when we use the electroosmosis, we use the mixing principle based on this concept. So first, if you can make a certain flow, which has vertical circulating flow, and in addition to this vertical flow, if you can make horizontal flow, okay, then by the combination of this vertical flow and horizontal flow, you can make a kind of laminar, but still chaotic flow situation to make a good mix. Okay? And for the principle to make vertical flow, circulating flow, we are going to use non-uniform surface property. That means zeta potential is changed as a function of position. And then in order to make a horizontal circulating flow, we are going to change the electric field strength as a function of time. So time period forcing will make horizontal flow. So by making combination of vertical circulating flow and horizontal circulating flow, we are going to generate certain chaotic flow situation. So that is the goal. And in fact, many people use the modified surface property. So by changing the zeta potential, okay, the surface, they could reduce the dispersion, and they could generate this kind of shear flow, and they could make a circulating flow. Actually, this kind of idea was already available, and this kind of idea was already available. And so for the analysis, we considered four cases. First one, plain heat junction, and the second one, we changed the zeta potential. So this part is 0.1 volts, and the right part is minus 0.1 volts, something like that. Then we are going to change this, the 0.1 volts region like that, strength, measurement, then measurement like that. Okay, so to see the accuracy of numerical computation, we compare the concentration distribution with the fluorescence experimental here. Actually, when we solve this problem, which is a little bit smaller, I'm sorry, quite a little bit larger diffusivity. So in fact, the diffusivity of fluorescent dye is a little bit less than this. But as you can see here, at least qualitatively very nice results are obtained. In this case, we use just constant 10 volt here and 0 volt down there. Okay, then as I mentioned, in order to generate the horizontal flow, we change the voltage here as a function of time, and you can see here we can make a horizontal flow. And because of the electroosmotic flow property, the flow, there is no change in z direction, more or less. Then, the amplitude of oscillation here is a function of zeta potential. So, in some sense, you may check the zeta potential from the reference or something like that by using this kind of experiment. The good thing here is that this is the starting point. So fluid A and fluid B is right here. So the diffusion is minimal at this point. So this measurement is quite accurate. All right, and as you have seen from the PRL paper over here, so when we change the zeta potential periodically like that, we can observe the circulating flow. Okay, same thing. And when we okay, modulates as a function of time like that, strength gets larger and gets smaller. However, in this situation, even though there is a circulating flow near the surface, overall, the particle trajectory is not very interesting because flow is just parallel to this channel. Okay, so in this situation, we do not have horizontal mixing, so overall mixing efficiency is not dramatic. So we change it a little bit, slant fashion. So in this case, flow is a little skewed. So when we use this kind of slanted pattern, as you can see here, the flow pattern becomes much more complicated. That means mixing efficiency increases more than. So, but when we use the exact type, in fact, the mixing was not so good as the one is slanted fashion. But when we use this kind of slanted, non-uniform surface properties, they could increase the kind of mass transfer of same distance, but as you can see here, much more mixing occurs. Right. So this is one brief example. Then we generated helical flow by using electroosmosis. This work was done by students in my group and in Professor Yu's group. And for the microfluidic system, a lot of static micro mixers are used. And recently, the Harvard group published this helical flow generation by using this pattern, bottom surface. Actually, our problem and our idea is very much similar to this, but we do not use this mechanical pattern. Instead of here, our idea is this: by using main electric field, we are generating parallel flows. Then, in addition to main flow, by generating this kind of transversal flow at the bottom. So overall, at the bottom flow will be a little bit it will flow with certain angle like that. Then up here there is no extra force. So because of that kind of non-vertical, non-transversal, non-horizontal kind of mixed flow will make for helical motion. So that is the whole idea. We solve the simple Stokes problem with the split velocity approximation for the problem side. And vector field, as you can see here, when there is no transversal contribution, the flow is just in parallel to the flow direction. But when we use the transversal electric field, we could generate helical motion. And this is the kind of section view. And particle trajectories, when there is no vertical transversal contribution. But when we added transversal part, as you can see, mixing occurs. Like that. In this way, so by using electroosmosis and by modifying some surface property, we could generate several interesting flow phenomena. But the problem is that, as I mentioned, the speed is so slow. So in recent times, people are interested in the certain phenomena which is related to the surface tension. And that is the electrowetting. So let me talk about that a little bit. So as I mentioned, in order to use mechanical system, complicated to fabricate and expensive, and if you want to use mechanical phenomena like electroosmosis, we need to use several kilovolts and it's slow. So many people are interested in the surface tension effect, and we're going to change that surface tension effect by using electric field. That is the idea of electroosmosis. And this is the kind of picture from the certain famous movie. So as radius gets down, surface tension effect is the pressure difference between here and here is very large. So even though he's working really hard, he cannot break. All right. So starting point is the Young-Laplace equation. So at the triple junction point, we have this equation. The electrowetting process is nothing but the change of the interfacial tension between solid and liquid. So by applying electric field in the vertical direction, we may collect the charges near the solid surface. Then collected charges will make this kind of force. Then later on, the contact angle will be changing, sometimes from the hydrophobic fashion to the hydrophilic type. And actually, electrowetting is not totally new. And before that, a very similar concept was available. That is called electrocapillarity. So if you plug in such an electrode in the electrolyte, as I mentioned, the counter ions are collected here. Then the like ions hate each other, so they push upward. Then the effect of this pushing effect will be the reduction of interfacial tension between the solid and liquid. So this kind of concept was available already. But the problem was in this situation was that if you apply very strong voltage between this load and this electrode, then the current will flow, and electrolysis occurs. So the applied voltage was limited at this situation. So electrowetting, then what's the electrowetting? Very similar to this, but by putting some dielectric layer, insulating layer between this electrode and the electrolyte, we can increase the applied voltage dramatically. So by using insulator in between, we could apply very strong electric field. That means we can collect a lot of charge near the interface. So, as you can see, in this case, the contact angle is more than 90 degrees, but it used to be about 60 degrees. So hydrophobic and hydrophilic. So they use this kind of idea to actuate microfluids. Here, electrowetting occurs and here not. Then the contact angle here is smaller than the contact angle here. That means same pressure here and here, but the pressure here is a little bit higher than outside. But in this situation, pressure inside is much higher than this. So, inside the drop, we have a pressure drop here, higher pressure region, low pressure region. So that's why this drop goes on in this direction. That is the electrowetting mechanism. And many people use, and some people use to split the microwave and sometimes get together and rotate and pumping. But as you can see here, the response time is very short, so very quick response. That is the advantage of electrowetting. Same thing. Actually, in order to explain this interesting effect, they use the Young equation in addition to the Lippmann equation. Lippmann equation is nothing but this. So when we apply a certain voltage near the surface, the interfacial tension decreases with the increase of voltage. When we have certain surface charge. So by combining this Lippmann equation and the Young's equation we have seen before, we can, derive this famous equation. So the theta is the constant angle. Cosine theta, when we apply the voltage, equals, zero voltage case plus certain term which is proportional to the square of this voltage. So when they perform this experiment, in several cases, they showed this kind of parabolic result very faithfully, but sometimes not. And when they performed very careful experiment, they found that as the voltage increases, okay, this parabolic shape is not correct. In fact, near the zero voltage, behavior is more or less parabolic, but when we increase the voltage very much, the deviation is quite significant. And they use this kind of up and down actuation. But thus far, the unresolved problem in the actual reading is this phenomenon. As I mentioned, the theory predicts this kind of parabolic shape. So when the voltage is not very high, plus minus, okay, but when we use the really extreme voltages, okay, the real experimental result is quite deviate from the prediction. So this is called the contact saturation. So in recent times, many people are trying to explain this effect. So we took the picture. In recent times, we applied finite element to analyze that kind of effect. So this is the triple junction point. So we solved the Boltzmann equation by using the finite element method, and we computed the free energy of the total system. Okay, we solved this Boltzmann equation inside and outside with the given surface charge distribution. Then, in that way, let me go on quickly. So, in that way, we could predict certain quantity, which is called line tension. Okay? So, by predicting this line tension, we could understand this saturation phenomena. Okay? And as you can see here, this line tension increases dramatically as the contact angle decreases. That means when the contact angle is near 60s to 90s, this effect is negligible. So parabolic result is okay. But when the contact angle decreases like that, so this contribution is larger and larger. So this one is the kind of deviation from the prediction by the parabolic shape. Okay, so our modified result is this. So this is the cosine theta equals cosine theta 0 plus this one is the parabolic term which is proportional to the square of voltage. And this is the newly adjusted term. And you have seen this term increases as the contact angle decreases. So kind of resistance to the reduction of theta. That means the contact angle cannot decrease, okay, even though we apply higher voltage. So kind of little explanation about the saturation phenomenon. Okay. But we need to get some approval from reviewers outside. Okay. This is the and by using about 5 minutes, I'm going to talk about dielectrophoresis. Okay. So compared with electrophoresis, dielectrophoresis case, we are using the polarized dipoles. Okay. So we must apply very strong electric field. But so among several terms of electromagnetic forces, so dielectrophoresis using this term, polarized. So if you have some distribution of electric conductivity inside the fluid, by just simply applying electric field, you can control the flow. And sometimes if you have interface, you can make a certain interface force, okay, surface force, by using this one or combination, we can control the flow. And for the particle, we can transport. So this is the electric force for the usual particle. So in the electric field, polarized, then polarized charges affected by the electric field to generate this kind of force. Here, Q is the ratio of electric permittivities inside to outside. So if Q is larger than 1, then electric force direction is to the direction, increasing direction. Okay, in that case, we call it positive dielectric polarizes. And on the other hand, if this one is less than 1, then particle is trying to go to the lower electric field direction. In that case, we call it negative dielectric polarizes. So actually, they use the negative dielectric polarity force. So when we have a quadrupole of electrodes, okay, so at the center, electric field is minimal. So particles are collected at the center, okay? And if you have two electrodes like that, then this line, along this line, electric field is minimum. Here, strongest point. So we can align, okay, particles. So this one was from the CHE material last year. But on the other hand, DNA particles have larger electric permittivities than the outside electrolyte. So if you apply electric field, then positive electrophoresis occurs. So at the strongest point, we can attract DNA particles. Okay, so anchoring occurs like this. So then by applying certain enzymes to cut at the right position, so-called molecular surgery. So we may use dielectrophoretic forces to generate circulating flow for inside the block. So because at the interface we have two components of the surface forces. One is the normal component, normal stress part, and the other one is shear stress part. So electric field generates electrical shear stress. Then to compensate that electrical stress difference, we must have hydrodynamic shear stress. So that hydrodynamic shear stress generates the flow inside. And then in that case, by modulating this, the external field, we may generate certain chaotic circulating flow inside. By using that kind of mechanism, when we apply optimal frequency forcing, we could maximize the mixing efficiency. And as you can see here, when the forcing frequency is not just right, so too small, too high, in that case, almost no mixing. But when we use the suitable mixing of the suitable frequencies, we could obtain very good mixing, as you can see in this picture. In that way, this is the mixing efficiency, and this is the forcing frequency. As you can see here, at the certain optimal frequency, we could maximize the mixing efficiency.